All right, so our last section of our book, last section of our year. So we're going to talk about Stokes Theorem today. So the fourth of our four big ideas from chapter 15. So line integrals, Green's theorem, divergence theorem we talked about yesterday, and today's Stokes theorem. And all of this stuff, the stuff that we've been talking about, really the kind of the motivation, that what drove the development was to formalize electromagnetic theory. So these guys were trying to make electromagnetism mathematically formal, and that's where a lot of this vector calculus that we're doing came from. The drive was to describe electromagnetism. All right, so yesterday we listed a couple different versions of Green's theorem that we had derived earlier, and after we talked about Green's theorem, we derived a tangential vector version of Green's theorem. So we're summing the tangential component of a vector field around a curve in the plane. So let's just rewrite that. Just to remember it. So we sum around a closed curve f dot dr, the tangential component of f, and we use Green's theorem to show that this was equal to the double integral over the region enclosed by the curve of the curl of f dot k dA. So the sum of the tangential component around the outside of the curve was equal to the sum of the normal components of the curl over the interior of the region. So we're going to, Stokes' theorem extends this idea into 3 dimensions. We're going to sum the tangential component of a vector field around a curve that bounds a surface. So that's what Stokes' theorem extends this to 3 dimensions. So we're going to do like we did with the divergence theorem. We'll state it, we're not going to prove it. So Stokes' theorem tells us that the line integral around a closed curve of the tangential component of f dot dr, is equal to, in 3 dimensions, the integral over s of the curl of f dot n ds. And S is an oriented surface. Bounded by the curve C. And n is our unit normal vector. So what Stokes' theorem tells us is that the sum of the tangential component of f around the boundary of this surface is equal to the sum of the normal component of the curl over the surface. And again, this is an extension of the fundamental theorem of calculus. We have this quantity on the interior of a region, and it has something to do with another quantity at the boundary of the region. So we're extending the fundamental theorem of calculus in this instance with a surface and the curve that's the boundary of the surface. Questions on the form of Stokes' theorem. So we have a line integral and a surface integral, the surface integral of the curl of f. Now yesterday the divergence theorem related a surface integral and a triple integral. Usually the divergence theorem helps us because often evaluating the triple integral is easier than evaluating the surface integral. So it's easier to evaluate the triple integral and the surface integral. We use Stokes' theorem in two ways, depending on what the form of our problem gives us. So we're going to use Stokes' theorem in two ways. We can use it to simplify a complicated line integral. By turning it in, so we have a complicated line integral, we turn it into a surface integral. So we might have a surface that has some complicated boundary, and we want to evaluate the line integral around the boundary. We might end up having to parameterize several different curves to evaluate our line integral. The second way we are going to use that you might use Stokes' theorem is to simplify a complicated surface integral. And we're to have a surface integral, and I'm going to put of the curl inside parentheses, because Stokes' theorem tells us about the curl. So if we have a complicated surface integral that involves a curl, we turn it into a line integral. So if we're doing a surface integral and we have this complicated expression that we have to evaluate, this integral of the curl, we might be able to turn it into a line integral over the boundary, and that might simplify our problem. All right, questions on how we might use Stokes' theorem. So let's look at a couple of examples using Stokes' theorem. So we want to verify, in this first example, we're just going to verify Stokes' theorem for a particular vector field. For our field is minus y plus zi plus x minus z j plus x minus y k. So there's our field, and our surface is given by z equals 4 minus x squared minus y squared. And where z is greater than or equal to 0. So first off, what is this surface? Let's make a quick sketch of this surface. So we have a paraboloid. So we're up here at z equals 4. So I'm going to sketch a quarter of the region. So there's z equals 4. And in the xy plane, we have x squared plus y squared equals 4. So our boundary, our line integral that we would look for the boundary of Stokes' theorem is this circle in the xy plane. That bounds this surface. So in the xy plane, our boundary is the curve x squared plus y squared equals 4. So to verify Stokes' theorem, we're trying to show that the line integral around our curve of f dot dr equals the double integral over our surface of del cross f dot n ds. So we're trying to show that these two are equal. So we're going to evaluate the line integral and evaluate the surface integral and show that the two are the same. So for our line integral, our curve C is x squared plus y squared equals 4 in the xy plane, and z equals 0. Whoops. So to evaluate our line integral, we need to parameterize our curve. So how do we want to parameterize this? Polar coordinates. So r equals so we want to express our curve in terms of some single parameter. So so we want to parameterize a circle. How do we parameterize a circle in polar coordinates? Cosines and sines. So we have a radius of 4. So r of t is 2, or r of theta, 2 cosine theta I plus 2 sine theta j. Then we need our prime. Our prime is minus 2 sine theta I plus 2, I forgot my 2 here, 2 cosine theta j. And we need to express f in terms of our parameterization for our line integral. So f is minus 2 sine t I, or sine theta, minus 2 sine theta I, plus 2 cosine theta j. Remember, z is 0. And plus 2 cosine theta minus 2 sine theta. Okay. So there's our field expressed in terms of our parameterized curve. And we need to do, yes?
What did you get that for f?
F is minus y plus zi. Y is 2 sine theta, and z is 0 in the xy plane.
Okay.
So everywhere we have a 0, everywhere we have a z, we can just put it 0. Okay? For our line integral, we need f dot r prime. F dot r prime, in this case, gives us 4 sine squared theta plus 4 cosine squared theta equals 4. So we have a nice line integral to evaluate. So in this case, if we had to evaluate Stokes' theorem, because we have a nice simple boundary and our curve parameterizes nicely, we might choose to evaluate the line integral rather than the surface integral. But here we want to show that these are the same. So our integral around our closed curve of f dot dr is the integral of, and I'm just going to do this first piece, so I'm going to multiply by 4. Integral from 0 to, oh, I'm sorry, the 4 comes from here. F dot dr is just this. and 0 to 2 pi. And we just get 4 d theta, because our f dot dr is just d theta. So we get 8 pi.
How do you know to do it in terms of theta?
So we evaluate the line integral in terms of our parameter, what we use to parameterize our curve.
Right.
So since we had a circle, we parameterize in terms of theta. So this integral evaluates to 8 pi. And we want to show that that is equal to the surface integral of the cross product, the normal component of the cross product, or the curl, sorry. So now we're going to evaluate this integral. So first off, we need del cross f. We need the curl of our field. And for that, we use our determinant, and we get minus y plus z here, x minus z here, and x minus y here. And when we find our curl, this turns out nice also. It comes out to 2k. And for our surface, our capital G, our big implicit function for our surface, is z minus 4 minus x squared minus y squared. Is that right? Let me go back. Z plus, yes, plus x squared plus y squared. So this should be a plus and a plus. And del G. So what we're going to use for to get our normal vector. Del G is 2xi plus 2y j plus k. So del cross f, we're going to evaluate. We're going to take the dot product of del cross f with del G. And we get 2. So our surface integral is the integral over our region of 2 dA. And that equals 2 double integral of over the region of dA. What's a double integral of dA? Double integral of dA is just the area of the region. So the area of a region, our region is a circle with radius 4. So that equals 2 times, or sorry, radius 2, right? Pi times 2 squared equals 8 pi. So we didn't even have to evaluate the integral. And we showed that the line integral and the surface integral of the normal component of the curl were the same. So we verified Stokes theorem for that particular region. Questions on that example? All right, let's look at one more example for Stokes theorem. So we want to find the line integral over our curve of f dot dr, and we want to use Stokes theorem here, but we want to use we're looking for this line integral, where our field is z squared I plus x squared j plus y squared k, and our surface is given by z equals y squared from 0 less than or equal to x less than or equal to a, and 0 less than or equal to y less than or equal to a. So we want to find this line integral. First off, what is our surface? To find our line integral, we need to know what our boundary is, what our lines are, what our curves are. Right, so a parabola in the zy plane, so it's going to go like this, like that. And this is z equals y squared. And it goes along the x-axis, so it goes down like so. So we have half of this cylinder, and it says x goes from 0 to a. So here's x equals a, and here we're at y equals a. So in the xy plane. In the xy plane, our region is a square. So this is above a square in the xy plane. Now to evaluate this line integral, if we wanted to evaluate the line integral around this boundary, we would have to evaluate a line integral here, 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 and here. It would require 4 line integrals. We would have to parameterize each segment of the line integral separately and evaluate all 4 of the line integrals to find this quantity. So we're going to use Stokes theorem. Stokes theorem tells us that this line integral is the double integral of del cross f dot n ds. And we're hoping that this double integral is easier to evaluate than these 4 line integrals. So for the surface, g is going to be z minus y squared. And del g, to get our normal vector, is minus 2yj plus k. And now we need to calculate our curl. So we need our curl for our field, so del cross f. So we have our determinant of our partial derivatives. And we have z squared, x squared, and y squared. And when we find this determinant, it comes out to 2yi plus 2zj plus 2xk. Now we're going to do del cross f. For our integrand, del cross f dot del g. When we take the dot product, we get minus 4yz plus 2x. So that's going to be our integrand. So we're going to integrate the double integral over our region of minus 4y times z, but z is y squared. So we get minus 4y cubed plus 2x dA. And our region in the xy plane is a nice square, so our limits on our integrals are very nice. So this is the integral from 0 to a, integral from 0 to a of minus 4y to the third plus 2x dy dx. Nice easy integral to evaluate. When we evaluate this, we get minus a to the fifth plus a to the third. And I think this double integral is a lot easier to evaluate than those 4 line integrals would have been.
Would you ever ask us to do a line integral? How is that complicated?
There's one of the homework problems where it asks you to verify Stokes Theorem, and the line integrals aren't complicated. It's just there are 4 of them, so it's kind of tedious.
How would you do a line integral? You can just
So here I would say, along this line, I would say y equals 0, so that simplifies that. And you could just say x equals t.
oh, so
And then you'd express f, so y and z are both 0. So you'd only end up with f would just be t squared j, and dr would be dt. So that line integral would be pretty easy. On these sides, you would say that y equals z squared, x here, x equals a, and you'd write f in terms of that parameterization, x equals a. And so let's see, right, and then you'd have to find r prime for that one, find f dot r prime.
That makes sense.
Okay.
And for the one where it's going down on the tablet, would you just, it would be y equals z, or z equals y squared?
Right, and you could go from y equals a to 0. Yeah, so you kind of go backwards on that one, and that would work. All right, this brings us to, finally, we can give a physical interpretation to the curl, similar to what we did with the divergence. We decided yesterday that we made some arguments that said that the divergence, we can think of the divergence as flux per unit volume. The divergence tells us the flux per unit volume at a point. So we're going to do something similar with the curl. So it only took us all chapter to get to where we could get to an interpretation of something that we could calculate in the first section. So Stokes Theorem. Stokes Theorem tells us that our line integral of f dot dr is the double integral over our surface of the curl the normal component of the curl over our surface. Now we call this line integral, f dot dr, over our closed path, we call that the circulation. So, and the reason we call it the circulation, we've taught it's the tangential component of f around our curve. So it has something to do with our field making something turning. So we call this the circulation. So this tells us that the circulation equals the double integral of our normal component of our curl. Now let's think about a tiny piece of surface. We're looking at this integral, we're thinking of a tiny piece of surface, and we're assuming on that tiny piece of surface, f is approximately constant. The piece of surface that we're talking about is so small that f is constant, so we can assume that it's constant. So the curl is nearly constant at that little piece of surface, and the normal vector, the unit normal vector, is essentially constant on that tiny little piece of surface. The normal vector doesn't vary, and the curl doesn't vary. So we can say that the circulation is approximately equal to the curl of f dot n times the double integral of ds. So we're saying that this is that the surface is tiny enough that that f and our normal vector is constant over that little piece of surface. So the circulation is approximately the curl of f dot the normal component times the double integral of ds. And the double integral of ds is just the area of that tiny piece of surface. So we're going to say that the circulation, I'll divide both sides by that area. The circulation per unit area equals the curl of f dot n. And as the area approaches 0, we take the limit as our little tiny piece of area approaches 0. Then we see that the curl of f, so I'm going to say delta s approaches 0. So our tiny little piece of surface, the area approaches 0. That the curl of f dot n equals the circulation. So the curl of f, the normal component of the curl, tells us the circulation of f about n. So if we take the dot product of the normal component of the curl with our normal vector at that point, that tells us the circulation of our field about that normal vector. So the curl tells us the tendency of the field to cause a circulation about a point. And if we think about it in terms of fluids, like we were talking about yesterday, if we have a fluid, if our field is a velocity vector of a fluid, and we look at the curl at a point, it tells us the tendency of that fluid to rotate about that, or to cause a rotation about that point. If we put a little paddle wheel in the fluid at that point, the paddle wheel would turn based on our circulation. So that's what the curl tells us, the tendency of the field to cause a circulation or a rotation at a particular point. So our divergence tells us about flowing outward. The curl tells us about causing a rotation. Questions?
Can you give us a picture so we can see how this works?
Sure. So if we had a, if we're talking about a point here, and this is our normal vector. If we have a circulation about the point, it tells us that our field would look like something like this, causing a circulation about that point. So our field would make our fluid rotate about that point.
So if the field is flat.
So if we had a field that looked like this at this point, that would not tend to cause a rotation. If we had a field that looked like this, and our vectors went this direction on that side and that direction on that side, it would tend to cause a rotation. And if we calculated the curl of this field, at that point it would be 0. And if we calculate the curl of this field at this point, it would not be 0. Okay, it's a little hard to visualize, but it. All right, homework. Page 1133. All right. And let me give you a suggestion on one of these problems. On number 9, I suggest that you evaluate, it asks you to verify Stokes Theorem, and you end up with 3 line integrals. I suggest you evaluate your line integrals of f dot dr. You have a 3-dimensional vector. On this particular problem, I would suggest you do it as m dx plus n dy plus p dz, where f is mi plus nj plus pk. So evaluate your line integral in differential form, because I did it the other way without doing differential form, and I have an integral that I didn't evaluate. So it's not difficult. It's all polynomials, but you end up with a polynomial with like 9 terms that you have to simplify and work with. And if you do it with your field expressed in this form, and you do your line integral this way, it's much easier.
Mr. Gamer, are you going to give us your favorite problems?
Right. So the quiz goes 15.4 through 15.8. So that's Green's theorem through what we did today. I'll put chapter 15 review problems up, and when I finish, I'll look to see which ones specifically are over the quiz.
Are you going to give
Okay.
us those on Thursday?
No, I'm going to give you the chapter 15 review problems now. And that is on page 1143. Now the chapter 15 are not necessarily only for the quiz. These, I strongly suggest you use these to supplement that review packet. Like I said, the review packet is a pretty broad overview, but it's a little light on the stuff we've done, especially in the second part of chapter 15. All right, let me look at which ones of these are for the second part of chapter 15. So, I do. These problems are Green's theorem through Stokes theorem. Before that, it's all the other stuff that we did at the beginning of chapter 15. But these problems specifically are Green's theorem and divergence theorem and Stokes theorem. Let me see.
That